Category theory formalizes mathematical structure and its concepts in terms of a collection of objects and of arrows. A category has two basic properties: the ability to compose the arrows associatively and the existence of an identity arrow for each object. Category theory can be used to formalize concepts of other high-level abstractions such as sets, rings, and groups. Several terms used in category theory, including the term morphism, are used differently from their uses in the rest of mathematics. In category theory, morphisms obey conditions specific to category theory itself. Basic concepts. Categories represent abstraction of other mathematical concepts. Many areas of mathematics can be formalized by category theory as categories. Hence, category theory uses abstraction to make it possible to state and prove many intricate and subtle mathematical results in these fields in a much simpler way. A basic example of a category is the category of sets, where the objects are sets and the arrows are functions from one set to another. However, the objects of a category need not be sets, and the arrows need not be functions. Any way of formalizing a mathematical concept such that it meets the basic conditions on the behavior of objects and arrows is a valid category, and all the results of category theory apply to it. The arrows of category theory are often said to represent a process connecting two objects, or in many cases of structure-preserving transformation connecting two objects. There are, however, many applications where much more abstract concepts are represented by objects and morphisms. The most important property of the arrows is that they can be composed, in other words, arranged in a sequence to form a new arrow. Applications of categories. Categories now appear in many branches of mathematics. Some areas are theoretical computer science, where they can correspond to types, and mathematical physics, where they can be used to describe vector spaces. Utility. Categories, objects, and morphisms. The study of categories is an attempt to axiomatically capture what is commonly found in various classes of related mathematical structures by relating them to the structure-preserving functions between them. A systematic study of category theory then allows us to prove general results about any of these types of mathematical structures from the axioms of a category. Consider the following example. The class GRP of groups consists of all objects having a group structure. One can proceed to prove theorems about groups by making logical deductions from the set of axioms. For example, it is immediately proven from the axioms that the identity element of a group is unique. Instead of focusing merely on the individual objects possessing a given structure, category theory emphasizes the morphisms, the structure-preserving mappings, between these objects. By studying these morphisms, we are able to learn more about the structure of the objects. In the case of groups, the morphisms are the group homomorphisms. A group homomorphism between two groups preserves the group structure. In a precise sense, it is a process taking one group to another, in a way that carries along information about the structure of the first group into the second group. The study of group homomorphisms then provides a tool for studying general properties of groups and consequences of the group axioms. A similar type of investigation occurs in many mathematical theories, such as the study of continuous maps between topological spaces in topology, and the study of smooth functions in manifold theory. Not all categories arise as structure-preserving functions. However, the standard example is the category of homotopies between pointed topological spaces. If one axiomatizes relations instead of functions, one obtains the theory of allegories. Functors. A category is itself a type of mathematical structure, so we can look for processes which preserve this structure in some sense. Such a process is called a functor. Diagram chasing is a visual method of arguing with abstract arrows joined in diagrams. Functors are represented by arrows between categories, subject to specific defining commutativity conditions. Functors can define categorical diagrams and sequences. A functor associates to every object of one category an object of another category, and to every morphism in the first category a morphism in the second. In fact, what we have done is define a category of categories and functors. The objects are categories, and the morphisms are functors. By studying categories and functors, we are not just studying a class of mathematical structures and the morphisms between them, we are studying the relationships between various classes of mathematical structures. This is a fundamental idea, which first surfaced in algebraic topology. Difficult topological questions can be translated into algebraic questions which are often easier to solve. Basic constructions, such as the fundamental group or the fundamental groupoid of a topological space, can be expressed as functors to the category of groupoids in this way, and the concept is pervasive in algebra and its applications. Natural transformations abstracting yet again, some diagrammatic and/or sequential constructions are often naturally related, a vague notion. At first sight, this leads to the clarifying concept of natural transformation, a way to map one functor to another. Many important constructions in mathematics can be studied in this context. Naturality is a principle, like general covariance in physics, that cuts deeper than is initially apparent. An arrow between two functors is a natural transformation when it is subject to certain naturality or commutativity conditions. Functors and natural transformations are the key concepts in category theory. Categories, objects, and morphisms. Categories. A category C consists of the following three mathematical entities: a class ob, whose elements are called objects; a class hom, whose elements are called morphisms or maps or arrows. Each morphism F has a source object A and target object B. The expression F a B would be verbally stated as F is a morphism from A to B. The expression hom, alternatively expressed as HOMC, more, or C, denotes the hom class of all morphisms from A to B. A binary operation, called composition of morphisms, such that for any three objects A, B, and C, we have hom times hom hom. The composition of F, A, B and G, B, C is written as GF or GF, governed by two axioms. Associativity. If F, A, B, G, B, C and H, C, D, then H equals F, and identity. For every object X, there exists a morphism 1X. XX called the identity morphism for X, such that for every morphism F, A, B, we have 1B F equals F1A. From the axioms, it can be proved that there is exactly one identity morphism for every object. Some authors deviate from the definition just given by identifying each object with its identity morphism. Morphisms. Relations among morphisms are often depicted using commutative diagrams, with points representing objects and arrows representing morphisms. Morphisms can have any of the following properties. Imorphism F, A, B is a monomorphism if FG1 equals FG2 implies G1 equals G2 for all morphisms G1, G2. XA. Epimorphism if G1F equals G2F implies G1 equals G2 for all morphisms G1, G2. BX. Bimorphism if F is both epic and monarch. Isomorphism if there exists a morphism G, BA such that FG equals 1B and GF equals 1A. Endomorphism if A equals B. N denotes the class of endomorphisms of A. Automorphism if F is both an endomorphism and an isomorphism. AUT denotes the class of automorphisms of A. Retraction if a right inverse of F exists, i.e., if there exists a morphism G, BA with FG equals 1B. Section if a left inverse of F exists, i.e., if there exists a morphism G, BA with GF equals 1A. Every retraction is an epimorphism, and every section is a monomorphism. Furthermore, the following three statements are equivalent. F is a monomorphism and a retraction. F is an epimorphism and a section. F is an isomorphism. Functors. Functors are structural preserving maps between categories. They can be thought of as morphisms in the category of all categories. A functor f from a category C to a category D, written f, C, D, consists of, for each object x in C, an object f in D, and, for each morphism f, x, y in C, a morphism f, ff, such that the following two properties hold. For every object x in C, f equals 1f. For all morphisms f, x, y and g, y, z, f equals ff. A contravariant functor f, C, D, is like a covariant functor, except that it turns morphisms around. More specifically, every morphism f, x, y and C must be assigned to a morphism f in D. In other words, a contravariant functor acts as a covariant functor from the opposite category COP to D. Natural transformations. A natural transformation is a relation between two functors. Functors often describe natural constructions, and natural transformations then describe natural homomorphisms between two such constructions. Sometimes two quite different constructions yield the same result. This is expressed by a natural isomorphism between the two functors. If f and g are functors between the categories C and D, then a natural transformation A to from f to g associates to every object x in C a morphism A to x, f, g and D such that for every morphism f, x, y and C, we have A to y f equals g A to x. This means that the following diagram is commutative. The two functors f and g are called naturally isomorphic if there exists a natural transformation from f to g such that A to x is an isomorphism for every object x in C. Other concepts: universal constructions, limits, and colimits. Using the language of category theory, many areas of mathematical study can be categorized. Categories include sets, groups and topologies. Each category is distinguished by properties that all its objects have in common, such as the empty set or the product of two topologies. Yet in the definition of a category, objects are considered atomic, i.e., we do not know whether an object A is a set, a topology, or any other abstract concept. Hence, the challenge is to define special objects without referring to the internal structure of those objects, to define the empty set without referring to elements, or the product topology without referring to open sets. One can characterize these objects in terms of their relations to other objects, as given by the morphisms of the respective categories. Thus, the task is to find universal properties that uniquely determine the objects of interest. Indeed, it turns out that numerous important constructions can be described in a purely categorical way. The central concept which is needed for this purpose is called categorical limit, and can be dualized to yield the notion of a colimit. Equivalent categories. It is a natural question to ask, under which conditions can two categories be considered essentially the same, in the sense that theorems about one category can readily be transformed into theorems about the other category. The major tool one employs to describe such a situation is called equivalence of categories, which is given by appropriate functors between two categories. Categorical equivalence has found numerous applications in mathematics. Further concepts and results. The definitions of categories and functors provide only the very basics of categorical algebra. Additional important topics are listed below. Although there are strong interrelations between all of these topics, the given order can be considered as a guideline for further reading. The functor category DC has as objects the functors from C to D and as morphisms the natural transformations of such functors. The Yonnet dilemma is one of the most famous basic results of category theory. It describes representable functors in functor categories. Duality. Every statement, theorem, or definition in category theory has a dual which is essentially obtained by reversing all the arrows. If one statement is true in a category C, then its dual is true in the dual category COP. This duality, which is transparent at the level of category theory, is often obscured in applications and can lead to surprising relationships. Adjoint functors. A functor can be left adjoint to another functor that maps in the opposite direction. Such a pair of adjoint functors typically arises from a construction defined by a universal property. This can be seen as a more abstract and powerful view on universal properties. Higher dimensional categories. Many of the above concepts, especially equivalence of categories, adjoint functor pairs, and functor categories, can be situated into the context of higher dimensional categories. Briefly, if we consider a morphism between two objects as a process taking us from one object to another, then higher dimensional categories allow us to profitably generalize this by considering higher dimensional processes. For example, a two-category is a category together with morphisms between morphisms, i.e., processes which allow us to transform one morphism into another. We can then compose these bimorphisms both horizontally and vertically, and we require a two-dimensional exchange law to hold, relating the two composition laws. In this context, the standard example is cat, the two-category of all categories, and in this example, bimorphisms of morphisms are simply natural transformations of morphisms in the usual sense. Another basic example is to consider a two-category with a single object. These are essentially monoidal categories. Bicategories are a weaker notion of two-dimensional categories in which the composition of morphisms is not strictly associative, but only associative, up to an isomorphism. This process can be extended for all natural numbers n, and these are called n-categories. There is even a notion of omega category corresponding to the ordinal number omega. Higher dimensional categories are part of the broader mathematical field of higher dimensional algebra, a concept introduced by Ronald Brown. For a conversational introduction to these ideas, see John Baez, A Tale of N Categories.